Hi class, this is a practice problem for Module 5, and I will tell you up front, this is a little bit of a longer problem, but that's okay, that's why I'm recording this video. Okay, so in this particular case, we have we're trying to produce and purify this polymer, polypropylene fumarate, for an orthopedic application. It is synthesized in a methylene chloride solvent, that's what we see here, using a zinc chloride catalyst. So we have a catalyst, a polymer that we're trying to produce, and the solvent. Since it is potentially toxic to human cells, it needs to be rinsed, meaning the catalyst, from the polymer solution. After processing, both the polymer precipitate and the catalyst are dissolved in methylene chloride. Okay, so in this entire problem, we just care about three things: the polymer, the solvent, and the catalyst, and that's it. The polymer stream is washed into sequential units, wash unit 1, wash unit 2, with the solvent as shown in this figure. The system, in theory, should operate such that there is a reduction of an order of magnitude, or a factor of 10, in the weight percentage or mass fraction of the catalyst in the recovered polymer stream, so in this stream. Okay, so now the problem actually goes into details, and I'm going to write down all of those details on my diagram. So I'm going to start by labeling the streams. 1, I'm going to call them these 2, 3, 4. You can number them in whatever order you want. And I'm going to call this stream 5, 6, and 7. Okay. And then I'm going to write down what was given to me by the problem, right? So I know that M1 is 100 grams. 100 grams per minute. I know that the mass fraction of polymer here is 0.4, of catalyst is 0.1, and of solvent is 0.5. Okay, so I finished with this, and this. Then it says 80% of the catalyst fed to each unit lives in the waste solution. So, which it says, by the way, only has solvent and catalyst. So let me write that down. So these should only have solvent and catalyst. These should only have solvent and catalyst. And what this is saying is that the mass flow rate of catalyst in 3 is equal to 80% of the mass flow rate of catalyst in stream 1. And same over here, the mass flow rate of catalyst in stream 6 is equal to 80% of the mass flow rate of the catalyst in stream 2. I think that's what that means. Then at each unit, the catalyst concentration in the waste solution is the same as the catalyst concentration in the polymer mixture leaving that unit, meaning that the mass fraction of catalyst here is the same. So I don't know where to write this down, but so basically what this means is that here the mass fraction of catalyst in 2 is equal to the mass fraction of catalyst in 3. Same here. The mass fraction of the catalyst in 6 is equal to the mass fraction of catalyst in 5. I think that's what that means. And the units are operated such that the stream between the two wash units, this stream, has 65% polymer, and the product stream has 80% polymer. Okay, so I know this is 0.8, question mark, question mark. And then here, the polymer would be 0.65, catalyst, question mark, solvent, question mark. Okay, I think, highlighting that, we took care of that. Okay, so I've highlighted everything. I put everything on my diagram. And now it is asking, determine the mass flow rates of the two inlet solvent wash streams. So basically it's asking us to find the mass flow rate in 4 and the mass flow rate in 7. Okay, now let's think about the systems I could draw. I could draw a system that looks like this. That would be one system. I could do, I'm gonna do different colors just for the sake of it. Could do the second system, or I could do, right, kind of a bigger system that would include everything, right? Okay. So let's see where we could start. We're trying to get M4 and M7. There's a couple of ways I could go about it. I could start with a big system, but then I would need to know stuff about 1, about 5, about 3, and about 6. And right now I have a ton of unknowns. Or I could start with wash unit 2, but I feel like in wash unit 2 I don't really know that much about wash unit 2. But in wash unit 1 I at least know the full composition of everything when it's in the inlet stream. I actually know that there's no polymer here. There's only polymer going to stream 2, and I know that mass fraction. So this seems like I have a decent amount of stuff to begin right here. So I'm gonna go ahead and start working with that first system. Okay, so this is gonna be system 1. Okay, I know M1, right? Then the other thing that would maybe help me is if I wrote down counting equations for all 3 things that are in this system. So I could start by doing a counting equation for the polymer, which would look like this, because there's only polymer in streams 1 and 2. Same for the catalyst. Same for nothing else. Yeah, sorry. For the catalyst, that's going to be M1 catalyst minus M2 catalyst minus M3 catalyst is equal to 0. And for the solvent, it's going to be M4 solvent minus M2 solvent minus M3 solvent is equal to 0. And then, of course, there's my total mass accounting equation here. That's going to be M1 plus M4 minus M2 minus M3 is equal to 0. So if I can somehow find M2 and M3, I already know M1, I could get to M4. So let's see if there's a way for me to get to M2. And if I look at this, I think I can use my mass accounting equation for the polymer, right? Because I know that I can rewrite this as, so I'm still working with the mass accounting equation for the polymer, as the mass fraction of the polymer in 1 times mass flow rate in 1, and that's equal to the mass fraction of the polymer in stream 2 times M2. And I actually know that this would be 0.4 times 100 grams per minute is equal to 0.65, yep. 0.65 times M2. And so therefore I get that M2 is equal to 0.4 times 100 divided by 0.65, 61.54 grams per minute, sorry. Okay, so I have M2. Then is there a way I could maybe get to M3? I feel like I could maybe get there somehow if I take a look at my catalyst right here. Okay, So, one of the things that we know, right, if I go back up here, is I'm also given this information about the catalyst, the mass flow rate of the catalyst in stream 3. So let me calculate that. So we know that the mass flow rate of the catalyst in stream 3 is equal to 0.8 times the mass flow rate of the catalyst in stream 1, right? And I know that this would be equal to 0.8 times the mass fraction of the catalyst, 0.1, times 100 grams per minute. And so that would be equal to 0.8 times 0.1 times 100. And that's equal to 8 grams per minute. Okay. So I have that. Okay, and then with this information, I can keep working with my catalyst accounting equation, especially if I remember that the problem also told me that the mass fraction of the catalyst in streams 2 and 3 are identical. So what I mean by that is that if I go back to my accounting equation for the catalyst, I can get that W1 cat M1 minus mass fraction of the catalyst in stream 2 minus mass fraction times mass flow rate in stream 2 is equal to 0. Let's replace that with all the stuff I already know, times 100. One of the things that I know is, I don't know this, but I know this. And this is the same thing as this, 8 grams per minute. Because remember, this is the same thing as this. Okay. And that's equal to 0. And so if I solve for the mass fraction of catalyst in 2, that would be equal to 0.032. Okay. And again, remember, the problem tells us that this mass fraction is the same as the mass fraction in stream 3, remember? So I know that this is also 0.032. Okay. And now that I know the mass fraction and the mass flow rate, I can use this equation to solve for the mass flow rate in stream 3, which would be 8 grams per minute divided by 0.032. And that's equal to 250 grams per minute. I'm actually now going to go ahead and number all these steps so y'all can follow them a little bit easier in case you're reviewing these later without the video. Okay, and now that we have that right, then it's super simple. I can simply use my total mass accounting equation to get the mass flow rate in stream 4. Okay, so the mass flow rate in stream 4 is equal to M1 minus M2 minus M3, right? Oh, just kidding. Hold on. Let me delete it and rewrite it completely. Okay, it's M1 plus M4 minus M2 minus M3 is equal to 0. And so if I do this properly, I would get M4 is equal to M2 minus M3, plus M3 minus M1. Okay, and if we do that math, that would be M2 61.54 plus M3 250 minus 100. So 211.54 grams per minute. Great. Okay, we're halfway there. Okay. Now, the next thing we can do is pretty much rinse and repeat. We're going to do the same thing, but in this case with everything we know, right here in Unit 2. Is that the fastest way to do it? I think so. Yeah, I think so. Okay, so, whoops. We'll go ahead and start same as before. We're going to write our accounting equations over here, which are actually pretty similar to these ones, and go from there. So now system 2. So for system 2, I have, again, my polymer that's only in streams 2 and 5. So the mass flow rate of polymer in stream 2 minus the mass flow rate of polymer in stream 5 is equal to 0. For the catalyst, we have mass flow rate of catalyst in 2 minus the mass flow rate of catalyst in streams 5 and 6 is equal to 0. And this time around, it's different for the solvent, because now we have solvent in every single stream. Solvent plus solvent in, I think it was 7, yeah. Minus solvent in 5 minus solvent in 6. And we also have kind of our total mass accounting equation for the system. That's M2 plus M7 minus M5 minus M6 is equal to 0. So once again, I'm going to start with the polymer because I think that's easiest given all the information that I do know. And I know that the mass fraction of polymer in 2 times the mass flow rate is equal to the mass fraction of polymer in 5 times the mass flow rate. And I know that this is 0.65 because it was given to me. I know the mass flow rate in 2 is 61.54. And the problem also tells me that this is 80%. Let me just double check. Yep. And then times M5. Okay. So if I solve for M5, that is equal to times 61.54 divided by 0.8, 50 grams per minute. Okay, let's see what we can do next. Perhaps we can do something pretty similar. Yeah, that's right. Something pretty similar to what we did before, because we also know this, right? So similar to what we did before, with the catalyst, we know that the mass flow rate of catalyst in stream 5 is equal to, no, not in stream 5, in stream 6, yeah? Yep, in stream 6 is equal 0.8 the mass flow rate of catalyst in stream 2. So that would be 0.8 times whatever mass fraction of catalyst, 0.032, times the mass flow rate in 2. And so then that's equal to 0.032 times 61.54 times 0.8, 1.58 grams per minute. And I'm gonna do my little numbers again. Okay, then literally right now we're just doing the exact same thing we did in system 1 in system 2. So again, use the catalyst flow rates and accounting equation, right? So we know that the mass flow rate of catalyst in 2 times the mass flow rate of catalyst in 5 minus the mass flow rate of catalyst in 6 is equal to 0. And we know this is 0.032 times 61.54 grams per minute. We know this is mass fraction of catalyst in 5 times the mass flow rate in 5 that we found, 50 grams per minute, minus the number we just calculated, 1.58 grams per minute. And so that gives us that the mass fraction of catalyst in 5 is equal to 0.032 times 61.54 minus 1.58 divided by 50, 0.008. And again, the problem tells us that these two mass fractions up here should be the same. And so having that, right, I know now that I can use this, sorry, got confused for a second. I can use my mass flow rate equation to get the mass flow rate in 6. So that would be equal to $197.5 grams per minute. Okay. Then I have a couple of options. Now I know M2, I know M5, I know M6, and I can calculate M7 that way. That's what I'm gonna do. If you really wanted to and wanted to be really ambitious, you could also do a total mass balance on the whole big system, because now you know 1, you know 3, you know 6, you know 5, you know 4, and then you can calculate 7. But that to me seems like more math. So I'm gonna keep it simple. And I'm gonna use the total mass accounting equation here. And so I'm gonna do, so this gives me that M7 is equal to M5 plus M6 minus M2. And so then that would be equal to 50 plus 197.5 minus what's M2, 61.54, 185.96 grams per minute. Okay. So those are our two solutions for that part of the problem. Yay, M4 and M7. Okay, determine the catalyst weight percent in the final outlet polymer product stream. So that would be the mass fraction of catalyst here in 5, which we actually already calculated. So it's over here, but I'm going to write it in percentage form, so 0.8%. Turns out we had already calculated that. Okay, and last question, does the design as given achieve the order of magnitude reduction of catalyst weight percent in the polymer stream? So let's compare that. So at the start, we had a mass fraction of catalyst that was 10%. And then in the end, this was down to 0.8%. So yes, we were successful. Yes, success meant a reduction by 10% meant success meant getting the mass fraction of catalyst to be lower than 1%. And so we were very successful. Yay. Okay, now one last thing to mention is that let's say you wanted to double check that you did all your math right. If you wanted to do that, you could do the total mass balance for the whole system and it should give you 0. So let's try that. Let's see what happens if we try to do this. If we try to say that M1 plus M4 plus M7, M1, 4, and 7 are inputs, 5, 6, and 3 are outputs, and 2 doesn't matter in that system. Minus M3, minus M5, minus M7. Is that equal to 0? Let's do that math real quick. So that would be 100 plus M4 to 11.54 plus M7, 185.96 minus M3, 250 minus M5, 50 minus M6, 197.5, and it is exactly equal to 0. So yes, which means we solved this problem correctly. Thank you for following along, and I hope that was helpful in helping you understand how to set up systems with multiple subunits. See you in class.